Hello. In this video, we will see Lab 11, Optics 1, Activity 1. So the objective of this first activity is to measure the refractive index of a given material using Snell's law. On a following video, we will see how to play with the focal length of a convergent and divergent lenses. Okay, that would be Activity 2. So first of all, what is the refractive index? Well, imagine we are doing this type of experiment. This is something we can do every day with our mirrors, right? This is a reflection, right? What we have here is an incident beam, and as we can see, we can just have the reflected ray, reflected beam, having the same angle with the perpendicular to the surface. We call this the normal, right? But what happens if this ray enters into the materials? Okay, that's something we can see with water or any liquid when we have light coming through, right? This is what happens, and there are two effects here. First effect is that the speed of light inside the material is reduced. Light is slowed down, and the reason is that atoms and other particles inside the medium are stopping the light somehow. That's why the light goes slower, right? So the speed of light in matter, how do we characterize this light? Well, we can use a relative measurement, which is the refractive index. The refractive index basically is the ratio between the speed of light in vacuum, which is approximately 300,000 kilometers per second, and the speed of light inside the medium. And like we said, inside the medium, the speed of light usually is smaller than in vacuum. We cannot go faster than light in vacuum. So therefore, in general, this refractive index always is bigger than 1. So the second effect that happens when we enter inside the medium with a ray is that there is a deviation. Here we have on the bottom the incoming light from medium number 1, which is, for instance, vacuum. Vacuum has a refractive index of 1 because speed of light of vacuum is the same as the speed of light of vacuum, right? The ratio is 1. While in here we have, for instance, water. The speed light in water is higher, therefore the index of refraction of water is 1.33. There is a law relating the angles of the incident ray and the refracted ray, and this law is Snell's law. Snell's law states that the product of index of the first medium times the sine of this angle with the normal equals the product of the index of the second medium times the sine of this angle. And as we can see, we have this deviation. And that's something you can experience at home. If you have a glass of water and you just put a pencil or something, you can see that the image is deviated from the straight light, right? And we have like a bended pencil. So activity 1 has to do with this checking of Snell's law. So the materials we will use on a physical lab would be basically an optics ray table having this shape, for instance, prism, and a rotary stage. Basically, it's a 360 degrees ruler, right? We have to use as well a kind of a light source, for instance, white light or even a laser. Okay. How do we mount all these elements? Well, it's simple. We can use the laser or the white source directed to the prism, and with this rotary stage, we will be rotating this prism and checking the incident light and the refracted light, the angles that forms these two beams with respect to the normal. So let's see this on a real example, this video.
All right, Dan, what do we got going on here?
Well, we're going to investigate Snell's law. We have a light source that's producing a beam of light that is going through this D-shaped lens, and we're going to compare the angle of the incoming beam to the outgoing beam, and the relationship between them is called Snell's law, but you can't see the beam because of the lights. So let's bring the lights down, and then now you can see it. It's going straight in, and it comes straight out. So not a whole lot going on there, but as we rotate it, at some point you can see they're going in different directions. And so we're going to measure the angle between the normal and the incoming beam and the normal and the outgoing beam. And from that, we can derive Snell's law, which is also based on Fermat's principle that the light will take the path of least time from point A to point B.
So what do you mean by least time? Is it's traveling the same speed, right?
So one model would say that the light does slow down when it goes through the lens. And so for the light to go from one end to the other end, if it took a straight line path, that would take it longer than the path it's taking here because it'd spend more time going through the slower medium than the faster one.
Okay. Well, you want to go ahead and make some measurements here?
So how about we start off at...
What are the two quantities that we're going to be measuring again?
The angle of the incoming ray from the normal.
Okay.
And the angle of the outgoing ray from its normal.
Okay, perfect.
And this Pasco basic optics ray table helps us do that. So I'm setting the initial angle to 10.
Okay.
And the outgoing one, well, you may have trouble seeing that on the video, so I'm going to put a pencil by it. Looks like about 7 degrees to me, but let's bring the lights up so you can see.
Or maybe just...
Or I'll get out of the way. There we go. And so you can see it's at about 7 degrees.
So I'll enter that in our table. So the incident angle was 10 degrees and the refraction angle was 7 degrees.
Right.
Okay.
So let's go up another 15. So the incident beam is at 25 degrees.
Okay, that's already in our table.
And the outgoing one, if I put a pencil there, looks like it's about 16 and a half if you want to go to halves.
16.5.
And now another 15, so we're up to 40.
Okay, 40.
And the outgoing looks like about 25 and a half.
25.5 degrees.
And then another 15.
Boy, it's really starting to bend now.
And we're getting a little reflection off the front, or at least noticeable reflection off the front surface as well. That could confuse you. So now we're at 55.
55.
And the outgoing beam is at 33 and a half.
33.5.
And then one more.
70.
70. You can definitely see that reflected beam now. It's following the law of reflection. And this is the law of refraction. And so it looks to be at 39.
39. Okay, great.
So they have all the data. And so they can do the analysis to do a graph and come up with Snell's law and then use that to answer some of the questions in the lab. And so the rest of the work is for you.
So let's put this in practice with the simulator. This is a very nice simulator. If you click on it, you will get to the address, the web link, and we will do a simulation there. So the first time you enter into the simulation page, you will get something like this. You go down, and this is the simulator, okay? You can click here to have a full screen. And here you have a light beam and two medium. Top substance is one medium, bottom substance is a different medium. Mediums are characterized by their refractive index, where we can check vacuum, air, water, whatever. Let's check with air. Okay, it's almost 1. It's light is stopped not too much on air. That's why the refractive index is quite close to 1, right? In the bottom substance, we will use, it's an unknown material. This is something we don't know the refractive index from, right? And we want to calculate this. How do we do this? Well, we can just send a beam of light like this, and this beam of light will get reflected, having the same angle, and refractive. To measure, we just press here the protector, and we can just nicely place here, and we can measure, as in the video, the incoming angle and the refractive angle, right? You can do this at different positions, right? I want you to do it to 4 to 5 different angles, okay? You just move this to a different angle, press clear, and go again, right? And that will launch a new beam, right? And the same to different positions, okay? If needed, you can reposition the protector. So that's your goal. Your goal is to measure incoming beam, angular position from the normal, refractive beam, angular position, that would be your 01, 02, and N1 is something you know, depending on the top substance you choose. And with these 3 elements, you can calculate the 4th one using a line fitting, as we will explain. So here are the things you must do. Again, you want to run the physics classroom simulator for the refractive index, and you want to choose for top substance any known substance, for instance, vacuum, air, whatever you want, okay? And in the bottom substance, you choose a known one, for instance, okay? And you want to do this experiment, refractive experiment, at 4 to 5 different incident angles. And you want to measure the incident light beam and the refractive beam, okay? Angular deviation from the normal, okay? And using Snell's law and Excel or any other plotting tool, you do a line fitting to calculate N2. That would be your index of a known one, okay? Do not forget to take screenshots for your lab report, as well as reporting your measurements and the line fitting you will do in Excel, Google Sheets, or whatever other tool you want to use. All right? So that's all you have to do. Good luck.